But anyway, tonight we're going to talk about this interesting paper that came out called Scalable MatMul-Free Language Modeling. And there are several videos on it, and we will watch the one from the author. Our good friend Yannick has one out though, and his is pretty good too. So, I'll come back to that. Okay, this is what we're going to do. I'll just, for anybody that, just real quickly, like real quick, go over kind of the basics of building and training neural networks. I know for many of you, this is, old school, but if there's somebody else that watches this in the future, this might be useful. And then I'll talk about what the MatMul is, and then what MatMul-Free is, and then we'll watch this video on matrix multiplication free LLMs. Okay? All right. So, how do we go about building our neural networks? Well, these are kind of the basic steps, and this is kind of like machine learning 101 here. So, I'm sure a lot of you folks already know this, but, the first thing we got to do is go out and gather some data, and then we got to figure out what our model's going to look like. And then we have this training loop where we just keep passing the data through there and then monitoring how well our model is doing, right? And then magically, hopefully, we pray that eventually it reaches some sort of limit, or the error gets low enough, or we reach a limit. Like, my credit card has now maxed out. I cannot continue anymore. That's for you, Richard. I said that. Or, whatever, you have a problem here. We're stopping, and it's good enough. Or if you're like my friends over at Google, there is no good enough and there is no limit. So I shall train for weeks and weeks and weeks because hardware is free. We all know it's just free out there in the ether, available to us. I mean, these are guys that when I was working with them, they would just like, let's start building the project. Let's start it on 5 systems building, and run for 5 hours. And then, one will get finished in 4.5, and we'll take that one and we'll just kind of let the other ones just keep running for another hour or something like that. It's a very strange world to be in, but that's the world if you work there. Anyway, we have a training loop that we go through. We pass data through our model, and then we make predictions. And this is where the MatMul really comes into use, using MatMul. Measure the error, adjust the weights to reduce error, loop again, right? We all know how this goes. This is just how our lives are in machine learning and training. Okay. So that brings up a question. What is MatMul? MatMul is the contraction for matrix multiplication. And if you haven't seen this before, this is what we have. We have essentially row time columns we're working on to produce one of these values. So you can see here we have in the row A2, comma 1, 2, comma 2, 2, comma 3, and you can see A2, comma 1, 2, comma 2, 2, 2, 3, and it's row times column. So it's that. And based on position, this is row 2, this is column 1, 2, 1 here. So we're filling in that one. So to do this for the next one up here, we'd have to go to row 1, column 1 again, and we could fill in that one, and so on and so forth. But you can see we have a lot of multiplication of going on, and hence we're doing a lot of MatMul or matrix multiplication. And this is a bit of a problem. MatMul is not the most efficient piece. I mean, it has gotten much more efficient since machine learning came around, just because it is such a heavy operator in there. It uses a lot of memory to store these values, which we just saw in this big matrix, and that was a teeny 3x3. Richard, how big are the tables that you're running? How many rows are you running through?
Oh gosh, I don't even know. Really,
millions,
lot.
millions, tens of millions. Yeah, so virtually, that your models are really quite big then, in terms of how much MatMul you're performing. It requires performing a lot of multiplication on 16-bit values, so that's an expensive operation too. And then there's this crazy thing I found. I thought you guys would get a kick out of this. The big O for this thing is something on n times 2 to the 3.71188 Does that sound like that's out of somebody's PhD dissertation or something like that? There's something in there. It's less than, this was supposedly the best that they're achieving now, because, worst case is like 2 cubed, so it's a cubed, big O cube, so it's a lot worse. It's expensive training and a long time. And the majority of model training time is doing MatMul operations. So if we can reduce this or somehow shrink this time, we can train more models in the same amount of time, which is always a good thing. Any questions on that? Very straightforward. Okay.
A very quick comment.
Yeah, go ahead.
So it's a lot of operations, but in particular, of the operations, it's the multiplies, not the adds, that are expensive.
Mm-hmm.
And multiplying to 16-bit integers would be even slightly less expensive. But multiplying to floating point numbers is extremely expensive. And so that's the part that people would like to avoid.
Is that because of the mantissa hanging off the end there, or?
I mean, at the end of the day, you take the mantis and you multiply them in a similar way to the way you multiply integers, but then you do have the extra steps where you have to figure out how much your exponent changed. You have to add your exponents, and then you have to.
Gotcha.
Yeah, in Rust, they or on blockchains, they basically turn the exponents or the floating point into full integers by multiplying them, and then they multiply them together after. So you can optimize doing that, but it's like a lot of work.
Yeah.
Are you saying that that's a performance speed up they do by actually converting to int, or?
Yeah, so they don't have to worry about the floating point anymore.
Okay, so they convert the data prior to going through the loops and everything, or?
Just for like simplified blockchain stuff. It's just like trying to gain efficiencies, because like these are systems that are constantly running on like sort of sketchy hardware or whatever. So
Isn't that where you told me I should find my accelerator cheap or something? I thought you told me that.
heck no.
Okay. Anyway, go ahead.
I had a friend who worked at MIPS, and he did the floating point unit for them. Does anybody remember MIPS? The first risk company. He told me that that the floating point unit basically was a factor of 5 more hardware than the equivalent computations in integers. So if you can do it in fixed point, you're going to save about a factor of 5 on the silicon level, at the bottom.
That's impressive. That's good info, Julian. Thank you. Okay, so it is expensive and long time. Even with these speed ups, it's still going to take, and it is the majority of what we do in training time. All right, moving on. So how do we get rid of this? Well, what these guys are proposing is to get rid of the floating point numbers and switch over to ternary weights. So 3 states, -1, or 3 values, -1, 0, 1. Okay, and what they see when they do this is they get a reduction in memory usage of 61%, and obviously they've come up with ways of not doing multiplication, which is kind of cool too. We'll see that here in a moment. Okay, so this is oh crap, you guys
Gary,
are,
can you back up. I don't
yeah.
quite understand what that means.
What's that?
They replace expensive floating point multiplication with ternary weights.
Yeah, we'll get there in a sec, Roger. If you let me. And if I after,
yeah, I think
we'll get
it's
there
like,
in a second.
Like a compressed version of it.
Yeah. Well, this is it. This slide is it here essentially. Okay, so what they do is they have those 3 weights with the -1, 0, 1, and blah 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 blah. Then they go through, and I guess compress is a good enough name for it, Richard. Is that they compress into those 3 values. Then they essentially end up with, anytime you have x times some weight, if it's I sub j, it just becomes 1, right? So it's just x sub j, right? So the first case, it's 0 if it's this one, and it's just the negative if it's the other one. So it's kind of kind of interesting how simplistic it is, if you will, on how they're doing it. And this is if you want to write it, you know, when you're computing the Y matrix on the output side, and you're tweaking it, you can actually reduce it down to just kind of these two operations here, because you don't care about zero. Zero has no contribution, right? X times zero is zero, so there's no contribution. So you can just go with the equals 1 values, just throw them on the positive side, and the ones that are negative, just throw them on the negative side, and you could subtract them off. Now, obviously, this isn't going to work just directly, so we'll have to get a little bit further down the road on that. Questions, because this is kind of the heart of the thing.
I would call it clipping. You're clipping the weights, so each is either, you know, plus or minus 1 or 0. So if it's positive, you clip it to 1.
I don't know the exact, Julian. I really don't know if they exactly how they clip, you know, that or.
I wonder if, like,
Bennett?
Well, it's amplification and clipping, so maybe just call it, you know, signum, the signum function, I think.
Okay.
So,
Richard,
so one thing to be clear about this is that in these neural networks, when we talk about this, the X vector is still full floating point number.
Yes, yes, absolutely.
Right?
Sorry, Ted, I should have mentioned it.
We're only doing ternary on the weights. So this means that even if you only either have the X sub j, which is just copying the floating point number, or negative X sub j is flipping 1 bit where the sign bit is. So those are both very cheap operations. Even if you only have those down below, because you're summing over all j values from 1 to m, you still need to do a bunch of floating point additions or subtractions, as it were. And so you are still doing floating point arithmetic, but this is where we were talking about the fact that floating point add is way, 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 way cheaper than floating point multiply. And so this requires less silicon if you're doing a hardware solution, and this runs faster on any GPU, CPU, FPU, whatever.
Okay.
It really gets fast if you go to fixed point. In other words, you know, once you've done this much, now if you go to fixed point, everything is as cheap as it's going to be, because you know that's the fastest sum and difference.
Okay. All right, I'm going to move on to the other thing. Okay, so kind of what are the advantages here? We can run it on a lower scale. That should be cheaper hardware probably. You know, it's faster and cheaper. It lowers barriers. And, you know, the faster and cheaper we can iterate, the more models we can create, the more model architectures we can play with, we can train, we can try more ideas, and we can create better solutions. So I think that's kind of a win all the way around, you know, because right now, I think I may have a slide in here. Did I do it? Oh, okay. No, I may have pulled it. But, you know, I saw something that GPT-4, they're taking 4 months, I think they're taking to train it. And I don't know how much hardware they're throwing at it. But it's a 4-month, you know, on a major release to kind of rev something at that scale. So as we know, no model works perfectly the first time. We have to tweak them. We want to try out some ideas. I'd be really interested from a project management standpoint to understand what they go through, because literally that 4-month is like, if you're a project manager and you put this big chunk to build this damn thing, you've got to do everything you can to try to not screw that up or have it go south. You know, because it's like, oh, we're 3 months in and it crapped out and we have to start from scratch. That's not you know, your bonus is going to get bigger. You know, if you're the manager in that group, that's not good. So, you know, anyway. Yeah, so if we can screw up, break things faster, remember that used to be a term people always said, break things faster and, you know, go for, who said that? Something, was that Steve
That was
Jobs?
Facebook's Zuck.
Zuck said that? Yeah, break things faster or whatever.
Yeah,
And
it's
it
like
makes sense.
move fast and break things.
Move fast and break things. And it does, but if the break thing is like, oh, hell, man, we moved for 4 months and then we broke it, that's probably you're out of Facebook. Anyway, moving on.
Hey,
Okay.
hey Jerry.
Yeah,
Just a
yes,
quick
sir.
thing. I seem to recall in the author's video, which I don't know if you're going to play the whole thing or selected portions of it, but I think he was saying that they really use this ternary stuff in full during inference, but that they actually use floating points. So in terms of the experimenting, I'm not sure if the experimenting is necessarily much faster.
Okay.
Just to be clear.
Yeah, I was only going to play a segment of it, but we can get to it here. And you tell me if it's coming up. How's that, Ted? We'll pay special attention.
Can I follow up on that real quick, Ted? So is the idea that I train with I don't know, floating point 16 or something, and then I do some sort of processing on the weights to generate this this ternary thing, ternary weight?
Yeah. I mean, today when we go to 8 or 4-bit, the vanilla thing you do is you just truncate round to the nearest, whatever, right? The slightly fancier thing you can do is after you've done that, you might do a tiny bit more training to see what you're hoping is that your errors will tend to cancel out, that you round it up in one place, you round it down in another place, and they tend to just sort of cancel out so that you end up getting very similar answers. But once you have millions of these, billions of these, there can be places where that doesn't happen, where they tend to like pile up the errors and so then in that last little bit of fine tuning, you might, if they all piled up, then you might round something down in order to alleviate where they've sort of all piled up. I don't know any of the details. I don't think this paper went into details, but because going to ternary is so drastic, I think they typically do that extra step to say, like Julius was saying, you can basically just take the sign, you know, if it's absolute value is less than this, call it 0. If it's more than that and it's positive, call it 1. If it's more than that in the negative direction, call it -1. But then you probably will want to just do some kind of sanity check that you don't get some bad results in certain places.
So is this, how do I differentiate this from just compression down to 1.5 bits then? Is it paying attention to, I think when you compress down to a couple bits, you still expand that into like 4 floating point values, right? Is that the way the compression works?
I'm not familiar with it, so.
So
I think it is. I don't think it, well, Ted's looking up for the answer.
as if it were written on the ceiling. I think if you just change all your weights to ternary, the biggest problem that they talked about in this paper was that the query key value attention matrix becomes too rounded off, sparse, whatever, and your model suffers in performance. So basically what you're saying, yes, the simplest thing to do would be I can quantize to 8-bit, I can quantize to 4-bit. Why don't I just quantize to 1.5-bit or whatever it is, 1.58, whatever. And you can do that, but the performance just suffers too much. So then they had to actually change the architecture to an architecture that would support 1.5-bit and not perform like junk.
Okay,
Makes
got it,
sense.
thanks.
All right, I'm gonna move on here. Okay, here's a caveat on all this. So the biggest model these guys have built is somewhere in the 5 gigabit range or something like that. So that's pretty tiny by our standards today. So
Transformer style? GPT transformer style models?
To be real honest, Roger, I don't know the answer to that question. Yeah. He may say, we're going to watch the guy who's one of the authors' videos, so he may give us a little more information on that. In fact, we're right there. Yannick has a video on this. In typical Yannick, this runs about 45 minutes, and I think we had that long. Plus, it kind of goes back and forth, and he says a lot of places, I don't have any experience in this and stuff like that. So we'll, Jason Esregan, I guess, is one of the paper's authors, and this Yujian Tang is kind of the host. He's just here for a minute. So with that, I'm just going to launch the video, and basic rules that we operate on. Anybody just say stop, and I will stop the video immediately, and we'll discuss where we are from there. Okay. All right. Okay, there we are. Can you guys still see my screen? Good.
No audio.
Oh, no audio?
Not yet.
Crap.
You remember to check the boxes when you shared your screen?
Oh yeah, you have to select that.
Oh, crap. I bet you I did.
Unfortunately, you'll just need to unshare and reshare, and we can just wait for a few seconds while you do that.
Okay. So I just go to my Zoom control to do that?
Yeah, stop sharing. And
How
then
about, can I pause sharing, or do I have to stop sharing?
my understanding is you have to stop.
That's my
That. Okay, I stopped sharing. Still says it's recording.
Yep, that's fine. Just
Oh.
start sharing again, and then look for the checkboxes on the right.
Oh, dude, that's cool. Share sound, optimize for video clip, right? Thanks, Ted. All right, I'm going to hit the go button. You guys verify that you can hear everything.
When I saw that, when I saw what you guys had published, I was like, "This is
Can you hear it?
Yeah.
Okay.
Yep, loud and clear.
crazy. This is going to be awesome." So, you guys, today you've heard a lot about LLMs and making LLMs accessible and all of these different things. Well, I think you're about to hear one of the most interesting research pieces of research to come out this year. And the most compute-heavy piece of transform models like LLMs is the number of matrix multiplications that have to go into each call. And this is a huge blocker to LLM adoption across the board, whether you're going to be doing edge compute, whether that's GPU availability, or simply through raw power consumption. And so that's why I'm super excited to have Jason Esregian here today to talk about new research that could be a breakthrough for this kind of LLM adoption. Jason, I'm going to take your slides to the stage, and you can take it away.
Awesome. How's the audio? Can you hear me all good?
I can hear you just fine.
No, well, yeah, no, thanks for the invitation. Yeah, I appreciate you having me out to talk about these matrix multiply free LLMs. For a bit of context, I remember seeing Jan LeCun tweeting about how we need to divest, or academia needs to divest away from advancing LLMs because industry's got it covered with a hell of a lot more compute. So it was pretty cool when we kind of came across this, what I feel like is a bit of a breakthrough, because we're able to get some seriously solid performance with very limited compute. Of course, more compute is always nice. It's always nice to be able to take these techniques that do work with limited compute and just seeing how far they can be pushed. So that's where we're at the moment. But without further ado, let's dive into this preprint and see what it's all about. So for context, it's the first billion parameter scale matrix multiply free model to achieve language generation. This is a very high level overview of, I guess, self-attention on the top left, the operators required for the matrix multiply free approach on the right. And so we're going to break this down very briefly in order to get a sense of what's going on. At a kind of an arm's length view, the things that we did were threefold. So firstly, we took that bitnet approach. You might be familiar with Microsoft's work in ternarizing all of the parameters in an LLM and still getting really nice performance. Ternarize as in setting or constraining your weights to +1, -1, and 0. And in that case, your multiplication just becomes assigned accumulation, right? That makes sense, right? If you multiply some activation by +1, it's just the same activation. If you multiply it by -1, then it's just the negation of that activation. And in custom hardware, you would just kind of bit flip the leading bit to represent that. And if it's a 0, then it's a 0, right? Which just blast away all of the bits of your activation, replace them all with 0. So the point is, in hardware, you're able to implement ternarized operations as just signed accumulations. You no longer need a multiplier to be instantiated. Then the second thing that we did here was replace the attention map. So historically, self-attention is used to do some sort of token mixing in order to understand the relationship between words or syllables, or more generally tokens, and how they relate to each other across long sequences. That is a big part of why language models have been able to achieve the performance that they have been able to achieve, and why they can remember something you said at the start of a paragraph several pages later, or many pages later in the case of Gemini. So yeah, with BitNet, they did this ternarized approach, but the outputs of their, what they call bit linear operations, or bit linear layers, still requires some outer products and matrix multiplication with non-ternary parameters. So while they're able to do some really good stuff with the amount of high-level memory or DDR access that they might need there, there is still a matrix multiplication, and for reasons I'm going to show you in a moment, that requires a significant chunk of low-level memory or caching. So we went ahead and replaced that with some other matrix multiply-free approach. So we just replaced it with a linear gated recurrent unit, and things worked pretty well. Now, where BitNet left us was with this kind of theoretical model, which unfortunately wasn't released, but hopefully we've kind of compensated for the absence of BitNet being open source in this work. But they left off with a call to action and said, hey, this model doesn't work as efficiently as it could otherwise on a GPU versus some custom hardware implementation. So we call on the hardware engineers of the world to go ahead and optimize low bit width operations and more lightweight LLMs. So yeah, we kind of took that up on ourselves and built our own FPGA implementation of this model as well. And as a result, we were able to run this model at 13 watts with human readable throughput. So just to kind of like wrap this up, these first two things are what enabled this matrix multiply-free language model, and the custom FPGA implementation actually makes it useful, right? Granted, it is of course useful to still be able to have the knowledge that a ternary LLM is going to work effectively, but actually deploying it is something else entirely. And then, gives you something really concrete to work with in silicon. So with that being said, let's just kind of take a very high level view of what self-attention is. It basically just involves, yep, excellent, you can see my cursor. It involves parsing this token embedding. It splits off into 3 parallel dense layers, which generates your QKV outputs, your query key and value outputs. Your query and keys are going to be mixed together and then somehow used with your V matrix or V vector. And as a result of that, you ultimately generate one single output. Now, in the background of all of this, you need to store the outputs of your key and values, or you need to store your key and values, because they're going to be used in your next step, right? So once the next token gets passed to your model, so we'll denote this as x of t equals 1. This could be x of t equals 2, where the top part of our operations are going to be operating on the first token, then bottom row is operating on our second token. Then we need to be able to do the exact same operations, but we need to keep a perfect history of our k and v values. And then so that's called the KV cache. And the KV cache is going to increase with an increasing context window. So that's a result of having to do matrix-matrix multiplication. This is just a more sequential way to execute mat-mat-mult. Now, on the other hand, and so yeah, you just keep doing this until you've exhausted all of your inputs. So on the other hand, this matrix multiply free approach is quite different. There are some parallels here, but let's break it down. It starts off seemingly the same way. We have our input embedding. We're going to take our input vector, embeddings, tokens, whatever. We'll pass them through a linear layer, but this time it's a ternary linear layer. And as a result of being ternarized, any linear layer or any linear dense operation is just, like I said, converted into a signed accumulation. So replacing vector matrix multiplication with signed accumulation. So from a software standpoint, if you were to code this up in Python, it might feel like there is no difference. From a hardware viewpoint, you can get rid of all of your multipliers. So again, you probably want custom hardware to be able to exploit something like this. So you end up with a set of outputs from these ternarized operations. And then what you do is the following part, the way that this is all color coded, hopefully to make things make a little more sense. We're doing a couple of sigmoids and this tau operation, which represents a silu. We're going to end up operating on these using this linear gated recurrent unit, which is visualized here. I should mention, so this GLU, it's basically doing token mixing in the way that self-attention is meant to as well, just with cheaper ops. We tested a variety of token mixes, including Raku4's token mixer. It just so happened that this worked the best. And as a matter of interest, the Raku4 token mixer, which we report this in our appendix kind of as a negative result to hopefully avoid the research community from wasting compute resources doing experiments that we've already run and didn't end up working as well. The Raku4 token mixer has a series of exponential operations, some divisions, basically a bunch of transcendental functions. So given that added complexity, you'd think it would work better. It did not. So this is what we used. After a set of these Hadamard products and sigmoid operators, all we need to do now is cache a single hidden state. That hidden state here does not grow with context length. We're not doing any mat-mat-mult, we're not doing vector matrix mult. This hidden state doesn't need to grow. It just kind of gets projected to your next sequence step, and you just do the operation again. And so we've seen that this linear GRU can do really well up to context windows of 2K and thereabouts. And going beyond that, as far as I'm aware, it remains to be seen how well it can handle longer context windows. So we're very interested in kind of extending these experiments and seeing what needs to be done to keep pushing, I guess, these state-space class of models or linear attention-based models towards those ridiculously long context windows. So, of course, I'm
going to stop there. Any questions or anything on that? Hello, can anybody hear me? Oh.
Yeah, we're here.
Okay.
Yep.
Okay, just want to make sure people still could hear me and things like that.
Yeah. I had a question. The hidden state, maybe they'll get to it later, but I'm just wondering how large the hidden state is. When it's a big change between the transformer where you have a KV cache that grows huge, and in this model you're using just a hidden state. So, do you know how big
No, I don't have an answer. Ted, did you have anything you saw?
I didn't see it in the paper. If there's code, then that must have been shared. But I
believe they do have a code implementation for this, though, they published too. So.
I think Yannick didn't say in exactly these words, but one thing that was not clear to me at first in the paper is that basically, Roger, they're replacing the attention with like a Mamba type mechanism. And in fact, their mechanism is even simpler than Mamba's. So I'm actually a little bit concerned that this is not going to scale.
Yeah. Yeah, I mean, I like the hidden state model, but it seems like it doesn't need to be as big as a KV cache, but it's got to be pretty big if you want long context. And do they talk about, is it like in a transformer, they break it up into multi-head attention? I'm wondering if they had kind of a similar multi-headedness with respect to the hidden state.
In the
Or is it
paper,
just thrown
it's
into
just
one
a
big bump?
straight up regular LSTM GRU now turnarized.
Okay.
GRU.
Okay.
Okay.
Interesting.
All right, I'm going to move us along. Maybe they'll answer some of those questions for us as we go along.
There is probably going to be some level of trade-off by discarding that KV cache and doing something far cheaper. As of now, as of the 1K, 2K context, we're still good. We seem to still be getting performance on par with self-attention, so that's nice. So I don't know, a logical next question could very simply be, all right, we went through all of this effort to ternarize or to build this matrix multiply free LLM. Why don't we just ternarize a bunch of things that already exist, right? Can't we just ternarize pre-existing LLMs and get similar performance? No, the short answer is no. We see on the y-axis loss and on the x-axis the number of tokens that have been trained. We use Transformer++ in the blue line as a baseline for comparison. For a few reasons, it's the backbone of a lot of state-of-the-art models, including Llama 2, Llama 3, Mistral, and a few others. Of course, they extend it and do some more fancy tricks and whatnot to make it more effective. But it is still the backbone. And much of the recent literature on linear transformers, so we're talking Mamba and GLA, they've also used Transformer++ as the baseline for comparison, so we kind of followed that mantra. So with that being said, what have we actually done? I've been alluding to how perhaps this model is only good for custom hardware implementations, but we still have to train this. And I should mention this caveat that this matrix multiply free approach is during inference only. For training, we still have to do matrix multiplies and whatnot. We're operating with BrainFloat 16 numerical formats. So we still have vector matrix multiplication during training. Of course, I think that is still valuable because you train a very solid foundation model once, and then you have a billion requests per day that only need to run inference on that model. So I would argue that inference is probably the more the thing that is going to cost you more when you have such large scale demand. Now, having said that, we still ran a set of optimizations for GPU. And as a matter of interest, so what we did was we fused a set of the kernels to accelerate training throughput. This was actually done out of necessity, and it's the only reason why we met the Nurex deadline. I think we finished our 2.7 billion scale parameter model training run several hours before the submission deadline, and it was basically because we were forced to do some CUDA level optimizations to actually enhance training. But as a result of doing that, we were able to use 2x less VRAM and accelerate training by this factor, so 25% less training time. These plots here are just kind of showing you what a vanilla bit linear layer looks like and what this fused bit linear layer looks like. So just a bit more context, fusing the ternary linear layer along with the root mean square norm, which just kind of normalizes the output vector of the ternary operations. So on the left, this plot represents time versus batch size, and on the right, memory versus batch size. The fused approach is in orange and naturally does considerably better in both cases as your batch size increases. Then secondly, we also wrote our own custom CUDA kernel to accelerate inference, basically to just better leverage the ternary weights that we're using along with 8-bit integer activations. In doing that, we then also get GPU benefits for inference. And so we were able to get 10x less VRAM during inference. So this plot here is comparing the VRAM that uses Transformer++ against that with MatMul-Free. So that's on the left y-axis, and on the right y-axis, we just have the same thing with latency. So in this case, lower is better, lower memory, less latency, so all is good. The x-axis sweeps across a variety of model sizes. We've gone up to 13 billion. Of course, I should mention this 13 billion relies on randomly initialized weights. So this has not been trained. We're just running the model, assuming that we are able to scale up to that parameter size. So then following that, the question kind of becomes how scalable is this, right? Something's got to give whenever you're winning performance or efficiency. It's there's always something that we can do better, or there's always something that you're going to lose. So let me break this down for you. This top graphic here is taken from a preprint from scaling laws for neural language models from OpenAI. Let's start with this plot in the middle. It shows the test loss almost linearly decreases with an increasing data set size. They've given this curve fit as well. I guess if 0.095 was 0, then it would be, I guess, perfectly linear. The plot on the right shows something similar, but instead of the number of training tokens on the x-axis, the number of training tokens is fixed, and instead the number of parameters in the model is increased. And then the plot on the left is kind of like the product of these two things, the product of the data set size and parameters, and that gives you PF days, which is petaflop days. So it's more about how test loss drops with increasing compute. Of course, crank up your model size, you need more compute. Crank up the number of training tokens, you need more compute. So what is noted here is that for optimal performance, all three factors need to be scaled up in tandem. So empirical performance has this power law relationship with each individual factor when it's not bottlenecked by the other two. So inspired by that, we explored how this scaling law functions with our model. So down on the bottom here, we see the y-axis, we have loss, and on the x-axis, we have flops. Floating point operations per second. And you'll notice that these dashed lines kind of come in clusters of 2. So one of these is our model, the other is just going back to the Transformer++ that is not ternarized, so a BrainFlow 16 implementation of Transformer++ that we retrained ourselves. The lowest 2 curves are the smallest model, the 370 million parameter versions of Transformer++ and MatMul-Free. And then the largest 2, as you kind of move to the right, which requires more flops to train, are our 2.7 billion parameter models. So you'll notice that in all cases, these 2 models, these pairs of curves are really quite close to each other, and they get closer and closer as the model scale goes up. And so then you keep training. The dark line is what we actually trained, and then the faded transparent line is our scaling law projection. So once you hit this region between 10 to the 22 or 10 to the 23 flops, then the 2 are expected to converge. So that's all well and good. A valid concern could very well be that this linear extrapolation of the scaling law doesn't account for potentially saturating losses, right? So perhaps this just tapers off and doesn't hit this star point. And hey, that is a legitimate concern, but we have seen Transformer++ go up to 70 billion parameter scales. That's Llama 2. So we're hopeful that this will kind of keep going up. Right now, we are talking to a few people to try and get more.
Yeah, go ahead.
I'm a little confused about one point here. These graphs are talking about performance during training, right? But then I thought he was talking about earlier that this applies only to inference. And so I'm trying to reconcile that. Do you know what that?
I do not.
What are they
know
training?
that.
Are they training something that has ternary weights then?
So, yeah, it's a good question, Roger. So first of all, the name MatMul-Free is catchy, but actually they are doing matrix vector multiplication all over the place in this model. Okay. What makes it MatMul-Free is the fact that if your weights are ternary, you don't have to actually do multiplication. You just do the sums of the positives and the sums of the negatives.
Right. Okay.
So, but it is matrix vector multiplication. Okay. So during training, you use floating point numbers for the matrix vector multiplication, and then you just quantize them at the end to be +1, -1, and 0. Okay.
So they're not quantized during training.
That's right. And that's true for everything. So if you're using a 4-bit
Hmm.
Llama 2, it was trained with 16-bit mixed precision and then just quantized afterwards.
So,
So you're saying that's a common strategy, if you will, because
Yeah, that's
yes,
perfect.
okay.
I mean, other than, so we're replacing, is the implementation though implemented as this accumulated sum? Or is it implemented as a matrix multiply?
No, because when you multiply two floats, you need to do full floating point expensive arithmetic. It's
Yeah.
only when you have quantized it to ternary that you can exploit a cheaper hardware solution.
So,
Okay, so what's the point that they're making here then about the training?
Right. So if we did kind of what you asked about earlier and what he showed on that slide, is can't we just ternarize a regular model, Mistral, and then not bother with the goofy architecture changes? So that didn't really work. So what he's really saying here is that his goofy architecture changes at full floating point precision are what's being shown on these charts.
Okay.
Yeah, and forgive me,
So
I
it's
don't
not
know
the
if I could really.
MatMul ternary stuff right now. It's just using a gated GRU for attention essentially, and
Yes.
Okay.
So basically, if you take away the hype about MatMul-Free, okay, it's ternarized weights where we normally would have fully connected dense MLP type layers.
okay,
Okay. And
but it's trained as a full dense layer.
yep.
Okay.
And in fact, even when you train with 16-bit, quote unquote 16-bit, I think people say we trained with 16-bit. They didn't actually train with 16-bit literally. Okay. I think what happens is the weights are 16 bits and the gradients are 32 bits because the gradients can be very small and you just need that extra precision or whatever. So the truth is, we talk about 8 and 4 bits being smaller, but once upon a time, 16 was small. All of them are using, to my knowledge, 32-bit gradients.
Yeah. Okay.
So the training really doesn't speed up.
Hey, I have a geometric interpretation of these ternary weights. So, you're always seeing RMS norms. So that means your vectors are normally on the hypersphere anytime you come out of an RMS norm. And so what this does is then quantizes, it just basically snaps the grid to the hypercube. So you just deform, so you take all these vectors around a hypersphere and you just round them to the corners of the hypercube. And those are your ternary weights.
So I was thinking of a different analogy, Julius. So like if you have numbers on the unit circle for like complex numbers, right? So if you multiply by like an arbitrary something, then you're going to have to like do all the fancy calculations to see exactly. But if you if your rotations are always either 0 or 180 degrees, then you don't have to do expensive calculations. You can just say, I'm either going to keep it as is, or I'm going to reflect it, vertically to the negative side.
Yeah.
So whereas if you use full precision, then you could wind up anywhere on the circle, and you need like whatever, I don't remember, the cosine theta plus I sine theta, whatever. You need to do those complex calculations. But if you know your theta can only be 0 or pi, then you don't actually need to program any of that fancy stuff.
Yeah, and so that's the case for every coordinate. But when you have, a billion coordinates, then you've got a billion. You can jump to any corner, so you can.
Oh, I see. Yeah.
You can go 45 degrees or 90 degrees. As long as you stay on the unity. So each coordinate can only be plus or minus 1 or 0. So so you really have 3 states across there. So yeah, you got the origin as well as the cube. So you have the hypercube and the origin. Everything, all components have to be there. So I guess that does mess up the norm. So yeah. So if it would be that if you had only plus and minus 1, you would be snapping to the corners of the hypercube.
Right.
So 0 distorts that a little bit, but you don't do anything with that. So, but anyway, that gives you a good intuition. Yeah,
if you ever had the easier Rubik's Cube that was only 2 by 2 instead of 3 by 3,
that's the only one I have time for.
Then it's all the joints on that easier Rubik's Cube are possible, and then of course in higher dimension.
Yeah.
Good one. All right, I'm going to move us along.
And I just want to mention that I just have to add that just think about the superposition situation now. If you think you have a bad superposition problem on a pentagram, or on a hypersphere, now look what you've got. So a lot of vocabulary vectors have landed on top of each other, and a lot of tokens at every level just go snapping to grid on top of each other. So massive superposition problem.
We haven't really constrained the x's, right? Just the weights.
Yeah,
so
just the weights.
When I think of super positioning, I think of it in the state, the x or h state.
But they're subject to activation functions, right? So if you go through a signum or a tan h, then they're substantially clipped. Once they're sure where they want to be, they're pretty much plus or minus 1 or 0 and 1, unless it's ReLU.
Yeah. So one thing I don't know, Roger, is whether or not transformers, sorry, I don't know a better word, but transform concepts from one to another. Okay. So like I cannot think of a realistic example, so I'm just going to use something completely artificial, but that if somehow you had blueness and you had evenness, that it's going to, transform that into, fragranceness or whatever. You know what I'm saying? But if those are arbitrary vectors, then you need an arbitrary translation or rotation or whatever to move it. And if you're restricted to ternary weights, you might not be able to do that. Right? To the extent that all you're doing is saying blue plus yellow equals green, maybe all the info's in the blue and the yellow, and you just need to sum them. But if you're going to manually like grab things and move them, then you really need.
Well, if each weight is responsible, I mean, I can think of this as, I'm not quite sure the difference between a ternary weight and like 10, in other words, a 10-bit number versus 10 ternary weights, right? They add up, right? So it's like, how much do I add, right? It seems like you can achieve a lot more than just 1 or minus 1 if they're adding if they're all in the same direction, if you're adding them.
Yeah. At one point in Yannick's video, he kind of goes on a little bit of an aside saying, well, gosh, if you ever had like really fast ternary hardware, then maybe instead of doing something in full floating point, you could just have a bigger, higher dimensional vector and sort of pack things into the other dimensions instead of having, numbers with more resolution, you just have more of them. And so he was
Yep.
kind of getting at that same idea that, yeah, maybe if you just had twice as many ternarays, that's almost as good as having 4-bit precision or 8-bit
Right,
precision.
right, yeah.
Okay, I'm going to move us on.
Get more GPUs to make this happen, because yeah, we're a relatively small academic lab that are very much GPU limited. Another thing that is worth noting is that flops, the nomenclature of flops is true for the transformer plus plus case, but we're counting ternary operations in our approach as a flop as well. So in a way, each unit of computation that our model reports is already a lot cheaper than what transformer plus plus can achieve here. So I mean, if you were to normalize this to like energy for a flop or a ternary operation, then that would kind of set our MatMul-Free LM approach far more to the left. So we'd get far smaller losses for far less compute. So that's what I want to say about the scaling law. With that being said, let's go into some of the results that we achieved. On this side, we see the zero-shot accuracy of our model versus transformer plus plus on a set of benchmark data sets. I guess as your model scale gets larger, so in the top cluster, we have the 370 million parameter model. On the bottom cluster, we have the 2.7 billion parameter model. We list out the number of training tokens, the number of blocks, and the embedding dimensions. And as the parameter scale increases, as I mentioned before from the scaling law, we're now quantitatively seeing the gap between transformer plus plus and MatMul-Free also decreasing. Some things worth noticing here, I guess, is that this WGE Winogrand, this is a binary choice question, and the ARC challenge is a 4-choice question. So in those cases, in those two benchmarks, it's kind of like a coin flip or a 4-sided coin flip anyway, and doesn't quite reflect what I'm saying here, but we included it anyway because it is a standard benchmark. I also want to flag, if you were to screenshot this and go ahead and compare it against other similarly sized models, one thing that you need to account for is how many training tokens were used. So Gemma, for example, that was trained on 6 trillion tokens. Llama 3 was on 15 trillion tokens. Again, our resources in a small academic lab limited us to far, far smaller tokens, to 100 billion tokens. So if we wanted to scale up to 15 trillion, I will more than gladly accept donations for $1 million to make that happen. Now, we're relying on GPUs to train these models.
I don't know how much we want to go into this, but I guess we can. We still have a little bit of time. He's going to go into FPGAs, field programmable arrays. So I guess we can do.
Yeah, I find that interesting. So yeah.
Yeah, it is, because with these smaller models and things, maybe deploying 2 hardware, devices and things like that, maybe they're a good target for them.
I like the idea of optimizing small models because I feel like it'll be good use cases in the future. I'm finding the more that I narrow the scope of models and fine tune them to a specific task, and then have lots of models, as opposed to one big one, it makes it more efficient.
Yeah, and plus, if you were building a consumer level product or something like that, right? It'd be in a task domain that you would target, things like that.
Yeah, you're almost always doing some kind of tuning or RAG in order to do consumer level products.
Yeah, maybe you don't have to do RAG or things like that if you can get some of these things to work or something like that.
Richard, are you looking at smaller models like targeted at a very specific task, or are you kind of aggregating a number of smaller models and together that they're performing well?
So I'm using a framework that basically has like a state machine that is like programmatically controls when the model tasks get assigned, and then it will swap out the context of the model to be very narrowly scoped to just a single task, and then it will grab a fine-tuned model that's specifically tuned to perform that task, and then I just have a big library of them. And then so like this, it's basically like a big toolkit. It grabs the tool that it needs, and then like the model that is getting instructed to do the task only does that task.
Oh, very cool. Very cool.
Cool. And then you optimize it for that task, I assume.
Yeah, exactly.
Okay. Okay.
So that sounds like mixture of experts.
It's sort of like like really explicit mixer of experts. Yeah.
So
But
who
it's
does
like
the routing? So the
uh
routing layer is some
is
handwritten.
yeah, it's like it's written, it's like code. I try to offload as much of the uh, cognitive like overhead to the state machine wherever it's possible, and then just have the models be able to indicate if they think they're done, and then you have like an overseer that just comes and double checks everything.
Nice.
Interesting. All right, I'm going to move forward.
Of course, there's a set of gradient operations that need to be overridden, in that if I was to ternarize a full precision weight, then I need some sort of quantization aware training using straight through estimators. So I'm not going to go into the low level detail of the non-differentiability of ternary operators, but so ultimately, you need GPUs to train these models. But then inference can go GPU free. And if we want to test out something that really milks ternary operations, then what do you want to look at? Custom hardware. And so if we want to meet the Nurex deadline, then we have 3 weeks to make this happen. We wrote this all up in System Verilog RTL, so it's thoroughly, all the results that were in the preprint are thoroughly unoptimized. There's no DSP, so we're not milking the kind of tailored acceleration components on an FPGA, where there's no DDR bursting, there's no pipelining. We wrote a custom assembler for our custom instruction set, which was used to convert assembly files into an instruction ROM. And that instruction set included all the ternary operations that we needed. So if I was to kind of test performance across different embedding dimensions, so sweeping across D for different model sizes, then perhaps in a more interpretable set of numbers. So I mean, we've got runtime and projected runtime. If we were to access more values from DDR, energy power estimates from power profiling tools, in a more interpretable set of numbers, what we're getting is 23.8 tokens per second at 13 watts. In contrast, the brain operates at 5 to 15 tokens per second at approximately 20 watts. That's what it takes for me to talk about MatMul-Free through StreamYard. Again, there's no pipelining, no batching, so there is a lot of room for improvement here. This is, I really want to stress that this is thoroughly unoptimized. And so next, we also evaluated resource utilization. We tested the use of various core counts. And what I want to highlight here is the latency. So if you consider this latency of the core itself versus DDR, so we're showing that memory access is not the bottleneck, which is typically going to be the bottleneck in most of your neural network workloads. So at the moment, it turns out that the 3 required ternary accumulations, and in the paper we do call it a ternary matmul, those instructions take up nearly all of the total execution time. So in future work, if we were to introduce parallelism and caching to improve the ternary matmul execution time, then that could lead to a huge change in the balance between core and DDR latency. With all of that being said, I'm just going to kind of fly through a bit of a future vision of where I hope these models are going to go. But let's say that I have conventional self-attention on some hardware where we've got inputs streaming into some accelerator, and then we've got outputs coming in. Given the large KV cache that is needed, so I mean, how many H100 GPUs do I need to serve one single user at 8-bit floating point at a throughput that matches human reading speed? So a semi-wiki estimate was 256 GPUs. Now, how many daily visits does ChatGPT get? There was some number that said 1.75 billion at its peak. Of course, that disaggregates somewhat. Now, this kind of darkening of the inference fabric just indicates that you're fully utilizing all of the hardware that you have available to you, right? Now, if instead we go into the direction of alternative models, so the precursor to this MatMul-Free paper was this Spike GPT model, which had some temporal sparsity and used state space approaches, etc. We released it about a year before our MatMul-Free work. Now, if I was to take some sort of temporally sparse, time-varying self-attention mechanism, And the idea is this, I mean, if you have sparsity in weights or in your data flow, then you might not need to have to fully utilize all of your hardware. So you can kind of run parallel workloads concurrently. You can basically do this multi-tenanting where many users can execute on the same hardware. So SNNs refers to spiking neural networks. It's a big part of the work that we do in our lab, where you just have neural networks with a high level of temporal activation sparsity. In that case, you're only accessing data that needs to be accessed, so you have less data movement, but low utilization. And hardware engineers and silicon guys, they hate to see low utilization. They don't want things there that aren't being used. So if we combine that with some sort of vertical cache or some memory that's stacked on top, then you're able to concurrently access all of your data that needs to be accessed. And so you end up getting energy benefits that are massive as a result of this parallelism. So with that being said, I kind of see that MatMul-Free could enable huge concurrency on the same hardware, especially if we were to push this towards some sort of temporally sparse neural network. This work was led by Rijia Zhu over in the back here. He did an incredible job kind of seeing this to fruition, and a lot of sleepless nights. There's a fantastic quote that the next greatest advance in neural networks is not going to be from some large, incredibly well-funded company, but rather from a grad student. And so I don't know, I couldn't help but think of that quote when Rijia was blasting out these results. It's yeah, really quite cool to see in doing so well. And of course, got to say thank you to the lab that actually makes this work possible. So with that being said, thanks very much. Forgive my 17th of June typo. And the wrong title. I'm clearly sleep deprived on this, but yeah, thanks a lot.
Oh wow, that was like really interesting. At least for me, and I had a bunch of questions I wanted to ask, but like primarily.
Anyway, do we want to go through the questions, or should we leave it at that?
We could probably leave it at that.
Yeah, I think there'll be question, but maybe we should have our own discussion then about things. I can stop screen sharing here. Is there stop sharing? Pause sharing? No, I don't want to pause. Stop. No, I don't want to stop share. God, look at this thing. It's got, anyway, I'm gonna stop sharing. Okay.
Jared, did you look, you said the code was available for this?
Yeah, in their repo, they have some code that you can play around with.
Okay.
And if you read the original paper, it has a link to the repo. So that's where I'd go if I wanted to play around with it.
Okay. Yeah, I wonder if some of the questions could be answered there.
Yeah, I don't know. Do you have any experience with FPGAs and things like that? I have zero, so.
Real minimal.
Okay. I know you do more hardware than I've ever done.
Yeah,
so, yeah. Okay.
And I don't know. I mean, the way he was describing it, he talked about our instruction set and assembler and stuff like that. So it almost sounded like they built a little processor.
Well, I thought when you bought the FPGA, it had like a processor on it, and then you could kind of layer your own instruction sets on top of it and then use those instruction sets in your programs. That's kind of how I thought they worked.
Yeah, I think it's kind of like programmable wiring between different types of units.
Yeah.
The units have gotten more complex, I think, over time.
When they're not just JK flip-flops or anything.
Well, no, I think it was, at least initially, the smaller ones were that, just little.
Yeah, that. I'm just kidding. I saw those maybe like 20 years ago or something like that, right? Yeah, but that's the last time I've used any of that stuff. So.
Yeah.
Now they have pretty big libraries. They have a lot of cells that you can bring down, and whatever will fit on your chip. Yeah, there's some audio work going on in that area.
Is it, Julius? Is the hardware though? Is it is the parts that you're connecting? Are they, like would there be an accumulator or a floating point multiplier or something like that? Is that the types of units that you have now?
Yeah, I haven't seen floating point, but yeah, you have adders and multipliers and various kinds of tables and just all kinds of primitive building blocks that you might want to use to make something bigger.
Yeah.
So my understanding is that it's a lot like, you know, a hardware description language, but
Mhm.
they're, you know, building up libraries of, you know, macros that you can then assemble and lay out and use up the gates that you have, you know, map it to the IO pins that you have and so on. Yeah, there's the Xilinx toolkit, and I have some friends who are working. I've seen a few presentations. I have some good pointers if anyone's interested in,
Yeah.
you know, getting a set of links in this area.
Well, I think it's interesting, the FPGA though, for this small model, right? Because that is a very power restricted, memory restricted platform, you know, so that may be why they leaned kind of that way.
Did they ever say what size model they had on the FPGA?
I did not hear that. It may be in the paper, but I did, you know, I did not hear it. I have not read completely through the paper either, so
Yeah,
I have to.
okay.
Get that. So, but anyway, I thought it was kind of interesting, and I was trying to think where you would use this, and the FPGA, you know, or that level of a hardware type dedicated box to do a task kind of seemed like a reasonable place to go.
Yeah. Yeah, it kind
Yeah,
of
I've heard
seems
that
like sorry, Julius, go ahead.
I was just going to say this. I've heard that it's used for very rapid deployment of custom hardware. Cisco used them in routers a lot, I was told. So it's also for like small volume ASICs. You know, it's like you're instead of, you know, sort of the competition would be making your own application specific integrated circuit, but that's a big turnaround. And so it's for a very quick deployment of hardware. But it's, you know, not the most efficient. You know, it's much more powerful than software in terms of, you know, throughput and parallelism and low latency and all that good stuff. But, you know, compared to an ASIC, it's a bloat. You know, it's a lot of extra stuff. So
Probably
but if you're high enough volume,
Yeah.
you know what you want, you can go into the high volumes, and you would go to an ASIC. That's my understanding of kind of where it sits.
Yeah, that's kind of mine too, that this is more of a, I won't say a one-off, but a lower production number type thing, and something you may end up revving over time too.
Yeah.
You know, because you can, you know, just blow it away and overwrite it, you know, in the field. So
Every
And I
time a
think
new model is trained.
you can eventually, I think you can eventually take the same Verilog code and generate ASIC from it. So it kind of gives you a proving ground
Yeah.
for what you might want to commit to ASIC.
yeah, that makes sense.
Rapid
think-
prototyping.
I kind of feel like this paper kind of threw too much into one paper, though. I mean, this whole idea of the GRU, using the GRU kind of in a Mamba style, they didn't really dive in too much what that meant and how it performed or anything like that. That could have been a paper on its own. The FPGA, kind of the same way.
Well, I think, you know, he alluded to that, right? That we were rushing to meet certain requirements, you know, of getting a paper submitted and things like that. And since I assume the speaker today was like the professor running the lab or something like that, that he's got, you know, some of these guys are graduating out and going into industry or wherever they're going beyond this or two, you know, and, you know, it seemed they're very time constrained, which is, you know, a lot of great work in school just goes to waste when the principal researcher just kind of goes away or goes on to someplace else or get a professorship over at another competing university or something.
Or a student graduates.
Yes, well, yeah, yeah.
Once you lose a student, who's going to do it? Who's going to do the work, you know?
Yeah, it's, you got your
I'm pretty
teaching
sure there's
load
always
right to
new
do.
students, isn't there?
But the problem is new students have new ideas, so they don't want to work on anybody
Right.
else's project, right? Is that what you've experienced,
Yeah.
Julius? That's been my,
Yeah.
you know, I haven't ever taught, but being a grad student myself a few times, you know.
I'm very not.
whenever possible. And very not.
Oh, I'm very not formally trained at all. So I'm very like I would be like leveraging the students' wacky and wild ideas and trying them out.
Well, no. I would assume, and Julius, you know, you do this for a living, but your instructor would probably point you at that information and leave it up to you to, you know, to pick up or move away.
There are two basic models that I know. So in EE, or even CS, usually you have grants, and the professor has the grants, and there's certain work that has to be performed. And if you want to be supported for a PhD, you're going to work on that, somehow or another. So there's a negotiation as to, what you're going to carve out as your dissertation work that's going to help deliver on the statement of work for the grant. But that's not the way it is in the School of Humanities and Sciences. So where I am, you just have students with a five-year fellowship. So you don't have the money, they have the money. And so you have to sell them, you have to inspire them, you have to recruit them, you have to cajole them. It's a very indirect thing. So really, you spend most of your time just kind of trying to keep up on what they're doing, and try to help them. You enforce standards of scholarship more than anything else. That's the way it works.
Yeah, give them the tools to be able to do the work, right?
Yeah. And you really want them to work on what they're excited about. So the passion really gets the best work, and so you just try to be as enabling as possible and supportive, and it's all interesting. So
Cool.
Very different model, very, very different. But you can also pull in a grant, and then you have the old model. So, I've had a few RA positions that were funded out of grants, and so we carved it up in a way that worked. And so I've had, I would say less than 5% of the students were doing that, but some of them.
Okay.